Tá bom. Então, pessoal, da aula passada vocês lembram de... Foi muita definição, né? Vocês lembram? A gente falou de tipos diferentes de acreção, né? De nucleativo de galáxia. Vocês lembram que é o disco de Shakura-Sunyaev? É o contrário. It's the opposite. Yes. So the Shakura-Sunyaev disk is the one that's geometrically thin and optically thick. It's the classical picture of AGN. While the RIAF, the radiatively inefficiently accretion flow, is the opposite. So we have a geometrically thick disk, but it's optically thin, so the radiation can escape. Okay, today we are going to take a deep look on synchrotron radiation, beaming, relativistic beaming, and inverse Compton scattering. How many of you are familiar with that? You are doing like that? I think you have some familiarity with this. Okay, so for the synchrotron radiation, I will start with this image of the Hercules A galaxy. So this is an optical image with the radio lobes overlaid. So most of the radio emission that we observe from active galactic nuclei, they come from radio emission. We can see they can come also from bremsstrahlung, but most of it comes from synchrotron emission. And if we have electrons spiraling in magnetic fields with non-relativistic speeds, we have cyclotron emission. If they are relativistic, we have synchrotron emission. All of this will be much clearer in the next slides. Okay, so our goal here is to compute the emitted power first for a non-relativistic charge and then for a relativistic one. Okay, so to derive the classical Larmor formula, we need to start. I will ask you to assume this with the retarded electric field. If you have a charged particle, it has an electric field that goes fades away with the R square. However, electromagnetic wave emitted by this particle fades away as 1 over R. Okay, so at long distances, the electric field is negligible, but we still have the electromagnetic wave. Okay, so to arrive at this formula here is quite annoying, and if you are curious, I would recommend you to take a look at the Jackson. Okay, but I don't think it worth the pain to do that in this course. But okay, this is very important to have in mind. The electromagnetic wave is given by the charge of the accelerated particle divided by the r, by the distance that we are from this particle, and the speed of light, okay? And this a here is the acceleration of the particle. If the acceleration is 0, there is no electromagnetic wave, okay? There is no photon. It will be clearer now. This is let's suppose this is a charged particle, and these are the electric field lines, okay? So if the particle moves, we see a ripple propagating in the field lines. Notice something very particular here. In this direction of the acceleration, the field lines are not drawn here, but how they change, how the field lines in the direction of acceleration change as the particle accelerates. We are seeing that these lines here, they change due to the retarded potential, okay? But if it's parallel to the motion, what happens to the lines? Nothing. Yes. So when a charged particle is accelerated, the radiation is emitted perpendicular to the direction of the acceleration. Okay, and the intensity depends on the sin of this angle. Okay, so save this, saves to this, okay? Okay, so the emitted power for a non-relativistic charged particle, we can compute that with the Poynting array, okay? Which you are very familiar, of course, with this formula. So for electromagnetic wave, E and B are perpendicular and have the same modulus. So we can write the Poynting vector like this. And if we substitute the radiation field that we found in the previous slide, here we'll find the formula for the total flux. Okay. Considering that we use this passage here as well. Is this clear? Okay. So this is just because I substituted the field that we found we assumed in the previous slide here. Okay. So this is the Poynting vector for the emitted radiation for an accelerated charged particle. Okay, this is more or less the picture. This is the formula for the radiation emitted, the energy flux. And imagine that the electron is in the center here, and it's going around this magnetic field. This donut shape here gives us the intensity of the Poynting vector. Okay, so in the direction of the acceleration, as I told you before, we don't have emission of radiation. Okay, but in a direction perpendicular to the acceleration, we have the highest values for intensity of the emitted radiation. Everything clear? Okay. Okay, so to find the total power, we can integrate the previous result over a sphere. Okay, this is the result we have with a sin square here. We can separate only the geometric or the spherical component. The result of these integrals here is 8 pi over 3. And maybe it's going too fast. Let me go back a little bit. Yeah, of course.
So in the point of view of general relativity, a particle following geodesic pattern does not accelerate. So we would see a radiation or not emitted by this particle following a geodesic.
By a charged particle. Mm. Oh, this is a very okay. Because if we have if you take a charge on your hand and you just spin, you emit radiation, even if there is no magnetic field, but there is acceleration. And okay, because you are going to general relativity, you are considering that there is no force, right? There's just it's just I don't know how to interpret that.
So in other point of view, a particle that is not moving in the gravitational field, they are actually accelerating in the point of view of general relativity. So we would see a radiation or not. You see, it's very confusing.
No, it's very confusing for you, and it wasn't for me, but now it is for me as well. I never thought about this from the general relativistic point of view. We do a lot of special relativity here, but not general. But okay. By the way, Marcela asked me something in the last class. You asked about the ionization of elements, right? Like oxygen 3, if the agent has no jet.
Yes.
You remember?
And I was asking how we get always the non-thermal.
Yes, okay. So the point the point was that instead of saying that we need non-thermal radiation, I should have said we need ionizing radiation. And then we can have ionized material there, close to the black hole, that was ionized by the thermal emission from the inner part of the disk or the hot corona, the X-ray corona. Okay, so at the end, the ionization was thermal, but not stellar, because the temperatures there in the disk are much higher than the stars.
And that gives it more activity than you.
Exactly, exactly. So let me continue here. I'll just do a pause here. Oops. Okay, so this was just the integration of the Poynting vector in a sphere around the electron. We just rearrange the integral, solve the angular part, and okay. And arrive to the total, this is the total power emitted by a non-relativistic electron, okay? Here you see that if the acceleration is 0, there is no emission. Okay, now let's generalize that in general, in special relativity. We need to start with the 4 vector. So we have the 4 velocity, with which is defined like this. So we have gamma in the speed of light and the speed of the particle. We can use this property of the derivative, that the derivative in the proper time can be written like this. This is the Lorentz factor. This is the time in the observer frame. So the acceleration is simply this derivative applied to this. Is this here? Okay. So for the time component, the first component is gamma c. So the acceleration is simply the derivative of this. And let's open this derivative now, the derivative of the Lorentz factor. This is the Lorentz factor. When we derivate it on time, we get this expression that can be simplified in that one. Okay, we can go slowly if you need. So rewriting the acceleration, the first component of the acceleration, we have this expression here. Did you manage to follow? It's quite fast. Maybe I can do it slower. But just a quick recap. So we just want the first term of the acceleration. In the end, we want the norm of the full 4 vector of acceleration. Let's compute the first one here. So the first component, after taking the derivative of gamma, which is this here, gives us this. Okay. Now, yes. No, vai tranquilo. Se tiver dúvida.
Não só aqui nesses slides.
Okay. So now we compute the first component of the 4 vector. Let's try to work with the rest, with the spatial component of the 4 vector. Okay. So the spatial component is just the gamma v. We can use the product rule here. Derivate first this. Okay. We can insert d gamma dt that we computed in the previous slide. And then we have that the component of the acceleration for the 3 remaining components of the 4 vector is given by this here. Okay. And now we can finally compute the invariant a square, the norm of the 4 vector. We already computed this and already computed this. So the formula is at the end is a little large, but we can simplify this to this final expression. Okay. And by the to come from here to here, we use this identity here. Okay. This will be part of the problem list. Okay. Actually, the problem list will be very, very short. And the goal is more to make you go deeper in the argument than to try to, it will not be a track, okay? So I will ask you to do this passage, but it will be clear in the end of the slides. Okay, so the total emitted power for a relativistic charged particle. Let's find the motion of a particle in a magnetic field. So we have the particle's relativistic momentum, and this is the Lorentz force. Now we have an electron in a magnetic field. This is the Lorentz factor. And we can finally isolate the acceleration. Okay, so this acceleration we can use in the norm of the acceleration we found in the previous slide. Okay, so do you remember, maybe I can go back a few slides. Do you remember the Larmor formula for the power was 2q squared, 3c cubed, a squared. Now we substitute the a squared by the relativistic acceleration. Okay, and this piece here is just the relativistic acceleration. And the formula shows that the power radiated depends on the orientation of the particle movement with respect to the acceleration. So we have here two scenarios. So if the particle moves in the same direction that it accelerates, then the power, this goes to 0 if they are parallel. And then the power is proportional to gamma cube 6, okay? If they are perpendicular, then the power goes with gamma 4, okay? If they are perpendicular, this becomes VA, V squared, A squared. This, we can put the A out of the brackets, and then this becomes 1 over gamma squared, okay? So we can cut here, and it becomes like this. Okay, this is exactly what I do here. So if they are perpendicular, like can be the case in the case of synchrotron emission, then this expression becomes this. We remove the A. This is 1 over gamma squared. We cut it. Okay. Now, a few slides ago, I showed you the derivative of the relativistic momentum in a magnetic field is equal to the Lorentz force. This is very clear, no? Then we isolated the acceleration, and now we can take that acceleration. I found it here. If you remember, if you don't remember this here, we can take this acceleration of a particle in a magnetic field, and we can simply substitute it. Yes, we can substitute it here. So substitute the acceleration here. We will have this. We can rearrange, and this is the final formula for the power emitted by a relativistic electron. Okay, so this is the synchrotron power. But we can even do better. Huh? So let's do it slowly. So the power, this is the formula for the power. It scales with the square of the Lorentz factor, making it a very efficient. The process of emitting radiation is very efficient for electrons. Yes. Yes.
Is this alpha the angle between the magnetic field and the velocity?
Yes, exactly.
But didn't you assume that the velocity and the acceleration were already perpendicular?
Wait. Here,
So
right?
are you looking to the general case, or you already did this?
Just a second. because I did the assumption here,
Yes.
exactly in this slide here.
Oh no, forget about it. No problem. Because the acceleration does not have the same direction in the brain.
Yeah, in the magnet field. Yeah, okay. Okay. Okay, so where were we? Here. Okay. So the power is scales with the square of the Lorentz factor, and is very efficient, especially for electrons. And you can see why there in the mass. This is the mass of the particle. So if you put a proton here, it will be 1,000 times more massive, and then the power will be much smaller. And furthermore, here we have at relativistic speeds, we have something called the beaming effect. Have you heard about the beaming effect? Or maybe in Portuguese, farol relativístico. Do you know what it is? No. On the last class. I will show you today. I can show you the math, how we arrived there. And I also did a small simulation. But in any case, this is the case of the cyclotron emission, as I showed you a few slides ago. In the case of synchrotron, which we have relativistic electrons, the emission is concentrated in the direction of the movement of the particle. Okay, so it's beamed. Okay, this is what we call relativistic beaming. So for an isotropic distribution of velocities, we can simply integrate this is beta, no? The beta we use in relative, so V over C. So we have beta square sin square of alpha. We can estimate the average power emitted by a single electron. Okay, if we simply integrate over all the possible angles, so we have beta square sin square the alpha. Beta goes out of the integral. We just have to solve this, and the average beta becomes this. Okay, so we substitute it back in the formula, and this is the formula that you find in radiative processes textbooks. So it's the average power emitted by a relativistic electron in a magnetic field. Okay, in CGS. I have a question. This is something that puzzles me. I don't know which kind of radiation is this emitted by the sword. It's a bit correlated to what you asked, but okay. I see a lot of radiation going around. He's spinning, but I don't think he's spinning relativistically. Okay, if you have comments on what's the possible origin of this radiation, let me know. Okay, now I showed you the average power emitted by a single electron. But at the jet of an AGN, we have a population, we have a distribution of energies for the electrons. These distributions, they can take several forms. One of the simplest ones is a power law. Okay, we'll take this one here, but in Blazer astrophysics, for instance, we commonly use power laws, log parabolas, and power laws with exponential cutoffs. Okay, but the easiest out of these three will be the power law. This is the one we are going to do. Okay, so what we call the emission coefficient, this J here, is obtained by integrating the average power of the electrons in the population. Okay. So
Is that things for another, or something like that? Why do you have this kind of form of?
why we have this kind of what?
Yeah, said that you have different forms
For the distribution. Yes. Okay. The power law actually is much more a simplification than a real. It doesn't bring us exactly the physics of the electron distribution. The log parabola, on the other hand, it brings the physics. So in an environment where the particles are stochastically accelerated, for instance, in a shock, for instance, the jet is shocking with the intergalactic medium, okay? In an environment where you have this stochastic acceleration, for instance, given by shocks, the log parabola distribution appears naturally. Okay, so the log parabola, yes, we have a physical reason behind. The power law with exponential cutoff as well, because sometimes you can have a cutoff in the production of particles above a certain energy. Okay, and typically this cutoff is related to the size of the source of these particles. So in an AGN jet, you expect the cutoffs to be very, very high energy because the jets are huge. In a supernova remnant, the cutoff is expected to be at lower energies.
So it stems from empirical stuff, let's say.
No, the forms of the populations for log parabola and power law exponential cutoff, they come from theory. But the power law is just an approximation, okay? But it's the one we will do here because it's the one that is more the easiest one. So before proceeding with this, we have to do one extra assumption, otherwise we don't go anywhere here. We do this monochromatic or delta approximation. Delta refers to the Dirac delta. And monochromatic, by this I mean that let's assume, to facilitate our lives, that all of the synchrotron power is emitted in a single frequency, okay? So the searchlight width of the synchrotron emission, this cone here, the opening of this cone is of the order of 1 over gamma. Gamma is the Lorentz factor. Okay, so the observer will see the electron, the radiation from the electron for a fraction 1 over gamma of its orbit. And because the electron is moving towards the observer close to the speed of light, we see a further compression by another factor of gamma, okay? So at the end, the duration of a pulse for us will be 1 over gamma square with the Larmor frequency. Larmor frequency is just how frequently the electron completes on orbit, okay? The Larmor frequency, which is given by this comes from the Lorentz force. And if we assume that our dt is the time interval between two, how do I say, crests, maybe, the maximums of of a wave. This approach gives us that 1 over t is our frequency, will be given by this inverted, no? 1 over t will be this here. So the observed frequency will be gamma square times the Larmor frequency. We will assume that all the power emitted by the electron is at this frequency. Okay, this is what we call the delta or monochromatic approximation. So we can write gamma in terms of the frequency, like this. And this is the same integral as before. This is this integration here, this integral here. I never saw, actually. Like, if you see the derivations of synchrotron emission, they will always use the monochromatic approximation. So this is the same integral as before, but in the monochromatic or delta approximation. Here we put the Dirac delta. However, the Dirac delta is in frequency. So it's frequency minus Larmor frequency, okay? Minus gamma square Larmor frequency. So we have to convert it to gammas, from frequency to gamma. That's why this factor here comes out. And then our final integral is this one. Okay. So let's solve this. We already found a formula for P, the average power emitted by one electron. We already have the formula for the distribution with which we assume to be a power law. And now we can solve the integral. We have the Dirac delta here, so the integral just vanishes, and we stay in this value here. We evaluate the functions in this value. These are the functions after opening them, and at the end we have that the emitted power from this population will go as a power law. Okay. And this is what we call the cutoff frequency, the Larmor frequency. Okay. Following? This will be online, okay?
Why do you call it monochromatic?
Otherwise, we can solve. Otherwise, it's...
Yeah, you assume any value, you basically have a spectrum here, right?
Or here, this is a spectrum.
Yes, this is a spectrum. So what do you call it monochromatic?
No, the power, the radiation emitted by a single electron, let's assume it's monochromatic. The population of electrons, every single electron with a different gamma will emit a different frequency. Okay? And then we will build our spectrum based on that. Yes, now yes, you're okay. I got you. So now we have this spectrum here. Okay, but better than showing the equation, I think, is seeing the plot. And let's compare the synchrotron emission with black body emission. Okay, so in the log space, this is the black body emission for a 10 to 5 Kelvin source. This is the synchrotron emission we found, is a power law, and this is a realistic case, okay, where we have synchrotron self-absorption. For electromagnetic waves at very low frequency, the plasma in the surroundings of the black hole or a neutron star, for instance, can absorb the photons. Okay, so for instance, have you all know what's a supernova remnant, right? A supernova remnant can be very hot for thousands of years because it's heated by typically by the neutron star, by the pulsar in the center of the supernova remnant. Do you know how the pulsar, like, is not the emitted radiation? It's a much more subtle that is similar to, that has everything to do with the synchrotron absorption. Imagine you have a neutron star. This is the spinning axis, and this is the magnetic axis. Okay, it's spinning, and since it has a non-aligned magnetic axis, you have always a changing magnetic field. Okay, this changing magnetic field will produce radiation, And the radiation, we have frequency at the same frequency of the rotation of the neutron star. So you can imagine mega waves, mega electromagnetic waves. Okay. And these waves, they cannot escape the plasma of the supernova remnant. They are absorbed by the plasma. So what we have in a supernova remnant is a sort of mega wave oven heating up the supernova remnant. And this radio radiation being emitted by the neutron star is not the radio that we see from the pulsar. We see the radio from the beams, okay, from the jets, from the beamed emission of the pulsar. These are other things. This is other radio emission. These are mega waves. They are absorbed by the plasma, and then the plasma heats up. Okay, it's the same phenomenon happening here. So for a synchrotron radiation at very low frequencies, the radiation is absorbed by the plasma. So the plasma heats up, but we cannot see the synchrotron emission. So what we derived in the previous slide was this spectrum here. Okay, was this line here. More realistically, we have this. Okay, synchrotron self-absorption. We see that all the time in the spectra of blazars. Sometimes the shape is not equal to exactly this, so we can see something like this, and then we can see a break here, and the rest goes up with another inclination. You know, depends on the distribution of electrons. Okay, this is the synchrotron self-absorption. I'm not going very deep here. However, the condition is that if frequency is very low, the medium is optically thick, and we have something like this, like the intensity goes up with the frequency to 5/2. If on the other hand the frequency is very high, the intensity goes as a power law. Okay, it was exactly what we saw in this plot. No?
The video, the peak of the synchrotron emission.
Okay, the peak of the synchrotron, it depends on the source. For a blazar, a flat spectrum radio quasar, for instance, it's a subtype of blazar. The peak is typically from radio to infrared. If you are analyzing a BLAC, the synchrotron peak can reach X-rays. They are very, very energetic. Okay, and you see why, I think, in the third lesson. Okay, why? Because in the case of flat spectrum radio quasar, the electrons in the jet, the cooling of the electrons in the jet is much more efficient, because we have a lot of extra radiation around that can bump in the jet. For BLACs, no, we basically don't have radiation outside of the jet, and then the electrons are not amortecido. How do I say? They are not break. Okay. Okay. Before starting this, we are going to do the relativistic beaming now, the derivation of the phenomenon. Is that clear up to now? Even it's not 100%, but later you can check the presentation online, or we can chat. Okay. Is that clear? Can I? Okay. So now we are going to see the relativistic beaming. Let's assume two reference frames. One is the lab frame, it's where we observe, and the other one is the frame of a particle emitting a photon or receiving a photon. I'm not absorbing. A photon arriving in this particle or being emitted by this particle. Okay. Okay, so the form momentum we can write like this. If you had special relativity classes, you're probably familiar with that. The Lorentz transformation along the x-axis, which is the axis of motion in this case, are those. We can simply put these two expressions together. So P0 is equal to gamma P line P prime 0. P prime 0 is this. So P0 becomes gamma with this, okay? Plus beta P prime X. Beta P prime X, which is this here. Okay, so this is just substituting the form momentum for the photon with the Lorentz transformations, okay? We have this. Okay, this is the expressions we just got. And to get the angle, we just need to take the P, the momentum in X divided by the hypotenusa, by the full norm of the vector. Okay, here I'm going slowly. I can show that to you later. For a photon, I don't know if you remember. Have you ever? You already did special relativity, right? Of course. No, Fisica 4. Yeah, Fisica 4. You see 4 vectors or something like that, right? Ah, you saw that, no? In Pernambuco. You too. Ah. Then you saw. Okay. Okay.
Maybe with electromagnet.
Okay. Yeah, electromagnet as well. Ah, okay. Okay. I'm asking you especially because I did my bachelor at the same institute as Marcella and also Paolo, and there I remember seeing this. Yes, but in any case, for a photon, do you know what's the norm? If you don't know if you don't have any memories, then it's not a problem, of course. But the norm of the quadrivector of the momentum is equal to the first component. Do you remember this? We can show even with the. Do you remember the total energy of a particle in special relativity? Do you remember how we write it? How do we write it? But what you say? E square.
And square C the power 4.
What's the formula for the total energy of a particle in special relativity? MC.
Yes.
It's like this, right? For a photon, what happens here immediately for a photon? 0, no? 0. Then this is the full momentum of photon. So the momentum for a photon will be the energy of the photon over C. Okay. And if we go back here, here in the definition of the four momentum vector, the first component is the energy of the photon over C. Okay. So back to our slides. To get the incoming angle, we just take cosine of the x component over the norm of the quadrivector, but the norm for a photon is simply the first component. We have these two components here. We just do the ratio of them. This is the ratio of these two components. Here we have some parameters that we can cut. So we can cut gamma, we can cut h in the prime over c, and the final result is this one here. And can you see what happened already? Just looking at this formula here. Remember that the prime is the reference frame of the relativistic particle. Okay, what happens if a photon is leaving this particle in the particle frame, is leaving at a 90 degrees angle? What happens with the cosine of theta prime? It will be cosine of 90, which is 0. So here is just beta. Here will be 1 plus beta 0. So cosine theta will be equal to beta. Okay, it will be better in the next slide, because we will do a more precise approximation of the beta. Okay, so the aberration formula that we just found, this one, in the ultra-relativistic limit, when gamma is much bigger than 1, means that this goes to 0, we can expand in Taylor. So beta is equal to 1 minus 1 over 2 gamma squared. Okay, so the case I told you, for a photon emitted at 90 degrees in the particle frame, the result is cosine theta equal to beta. Okay, but we can here write this in terms of gamma, and then we have cosine d theta equal to 1 minus 1 over 2 gamma squared. Okay, this will be another, this will be a challenge. I don't know, which time is it? Almost 3. I was planning to do that with you here, but it may be very boring. So, of course, you can do that at home to exercise. But we have, from the previous slide, we found that cosine d theta was equal to 1 minus 1 over 2 gamma squared. However, for small angles, we can also expand the cosine. So if we expand this in Taylor, you get this expression, ignoring the rest. And then we just equate these two terms, and we find that theta, the opening angle in the ultra-relativistic case, is simply 1 over gamma. Finally, we got to the opening angle of the synchrotron emission. Okay, that I showed you a few slides before. If you are the kind of person that in Portuguese we say, entendeu o que é que eu desenho, né? So this is not, I simulated this thing here. So I run this again. This is the rest frame emission of the particle. Okay. So in the for instance, electron, in the electron frame, it's always the same. It's isotropic. Okay. It can be actually. It can be isotropically. In the lab frame, if this particle is moving in that direction with respect to the observer, we start to see this beaming of the emission. Okay, there is even another phenomenon happening here that I didn't discuss yet, but we will discuss in the next minutes. Okay, can you see something else different in this spot? I'll run this again. It's not just the concentration, no? The Doppler effect. So the radiation is not only beamed, it's also boosted in energy, okay? So it becomes bluer in the direction of motion, okay? Here is the same thing done in 3D, just because I thought it was really cool. So Yes, in the direction of motion, the radiation is concentrated and is blue shifted.
So you are considering an accelerated effect.
Yes.
The radiation should be concentrated like around the 90 degrees angle, not in the direction of movement.
No. Okay. You have a magnetic field in the vertical here, and the electron going like this. Yes. So it's in the direction of the where the electron is propagated. Okay. Now we are going to do the inverse Compton scattering. Have you heard about Compton scattering? What's Compton scattering, Naomi? What? The atom absorbs an electron. No, this is beta decay. No. Photon is deflected by an electron. No? So we typically see that in X-rays, right? And for experiments, it's better to use high Z material, so the outwards electrons are weakly bound to the nucleus, no? So we can consider them free. But in any case, this here is the inverse Compton scattering. And what happens is straightforward. So we have a very energetic electron, a soft photon, and this electron will bump in this photon and will scatter it to very high energies. Okay. And you see for how much. So let's start with the Lorentz transformation of the time in the observer's frame. This is the observer's frame, okay? And the particle frame is this one. So it's a lot of text. We can easily derive the relativistic Doppler effect if we interpret the time interval dt as the time between the arrivals of two successive cycles of an electromagnetic wave with a frequency given by 1 over this time interval, okay? In the observer's rest frame, and nu prime equal to 1 over the time interval prime in the electron's frame, okay? So we can substitute this by the frequencies. This is 1 over frequency, so we have this. We can just invert here, change sides, and then this is the final formula. This means that in the electron's frame, the incoming photo energy, 18d prime, is multiplied by this factor, which is always above 1, okay? So we can imagine an isotropic distribution of photons, okay? And a relativistic electron passing, okay? Okay, it's exactly what I do in this slide. Okay, imagine this scenario. You have an isotropic distribution of photons in the observer's frame. If there is an electron relativistic crossing this field of isotropic photons, how does this electron see these photons? Will it see these photons isotropically? Based on what we saw in the previous slides on the beaming. What is the electron relativistic? I'm assuming the electron is relativistic. So what looks like an isotropic distribution of photons in the observer's frame, in the electron's frame, will be coming from the direction of the movement of the electron. That beaming effect that I showed you, it serves to emission or to receiving, I don't know, to how it sees the world, okay? If you are traveling close to the speed of light in your rocket, you will not see just what's in front of you, okay? You can see things that are behind. Okay, everything will be concentrated in front of you. Okay. So the same will happen for the electron. The electron will think that what looks isotropic distribution in my frame will be a very concentrated distribution of photons in the electron frame. Okay. So if the photons are scattered by a single ultra-relativistic electron moving along the x-axis, relativistic aberration causes most of the photons to approach nearly head-on in the electron. Okay. I think you like it, no? It looks like you like it. Yes. So they will approach basically head-on. We are considering an ultra-relativistic electron. So the formula was this one here. If they come head-on for the electron, cosine will be cosine of 0, which will be 1. Okay. So it will simplify our equation. Okay. So in the frame of the electron, the incoming radiation will be boosted by this factor here. Okay. And it will come only from the direction of the motion. We are in the ultra-relativistic case. Now it starts the very interesting part. In our frame, let me try to go slow with you here, because this can become complicated. So we started with an isotropic field of photons. Okay. For the electron, ultra-relativistic electron, these photons will not be isotropic, no? They will be concentrated in the direction, they will be head-on, no? The collision will be head-on, and they will be blue shifted. Do you agree? You guess so, okay. They will be blue shifted. When this photon interacts with the electron in the electron's frame, the electron will scatter this photon like any other photon, like a normal common Thomson scattering. Okay. And it can scatter this photon in any direction in its frame. Okay. And the energy will not change in the electron's frame. Okay. So let's suppose that the photon had the isotropic field of photons. Each photon has energy 1. Okay, doesn't matter the unit. Energy 1. In the frame of the photon, the electron, the photon arrived with energy 10. Okay, and it was isotropically scattered with this energy, 10. Okay. However, in my frame, I'm looking at the electron. This scattering cannot be isotropic because the electron is moving relativistic in the x direction. So the scattering in my frame will again be beamed. Okay, so we have beamed twice the original photons. Once for interacting with for entering the electron's frame, and other for when it's leaving the electron's frame. Okay. No? Okay.
Moderated. After that, then you are like back again in the standard reference frame. It's like that's the way I see it.
Yeah, but yeah, this is where I want to arrive. Let me this. I don't need to. Okay.
So if you put a black box in this direction, you don't know there is a Compton scattering occurring. So you have like a symmetry in the emitting and the observing photons.
No. I don't get it. I don't get this black box. Where are you putting this box?
You have the electron emitting radiation, and this radiation is being beamed.
Yes.
Right? And this is the problem. The only thing is happening that you know your interaction with the Compton scattering. So you have like isotropic radiation in your frame.
In the observer frame.
The electron
frame.
Frame.
It will arrive beaming.
This radiation is being beamed.
Yes.
So if
for other reason.
Yes, because of the Compton scattering, not just because of the frames. So in both cases, you have the radiation beam, both in absorption and the emission of the radiation.
Yes, the formula for the beaming, it serves for it's not absorption exactly, but receiving.
Yes, receiving. So I have a symmetry between the receiving and emitting.
It's absolutely the same formula. It's the same thing. So, summarizing, this isotropic field of photons in my frame, in the observer's frame, we will arrive basically only in one direction in the frame of the electron, and it will arrive there with a much higher frequency, okay, due to the Doppler effect. There, in the frame of the electron, it will be Thomson scattered. It doesn't change frequency in the electron's frame, and it can go to any direction that the Thomson scattering allows, okay? However, in my frame, again, I'm seeing this. This scattered photon will be beamed, okay? And I will see this photon being emitted in the direction of the motion of the electron. So what I see in my rest frame is isotropic distribution of photons, a single relativistic electron. The photons that enter there in my frame, they are still isotropic, okay? And then they leave always in the direction of the electron. Okay, so in my frame, what happens is this. Isotropic relativistic electron is scattered photons always in the direction of the motion, okay? The most confusing part is when we change reference to the electron frame and then come back, okay? But remember that in the electron's frame, we have the same effect, okay? So in the observer's frame, we will see the radiation that was scattered in the electron's frame, boosted by this factor here. However, the radiation that the electron saw was already boosted. So it was like this, okay? So we can substitute, oops, there was no zero here. We can substitute this here, and we get this as our final formula, okay? So the frequency that I will observe of a photon that was Compton scattered will be the original frequency of the photon multiplied by this factor squared, okay? We can simply, in the ultra-relativistic case, beta will become 1, okay, with 10 to 1, and beta 10 to 1, and then we have this. So this is the maximum energy a photon can have if it's Compton scattered, okay? This is the most optimistic case, no? The ultra-relativistic electron, okay? This is the maximum energy we can get. And what's fantastic here, at least in my opinion, is that the boost can be strong. Imagine you have an optical photon that is Compton scattered by a relativistic electron. The values of Lorentz factor for an electron in the jet of an AGN, they typically range from 100 to 10 to 8. You can have variations, but from 100 to 10 to 8. So you can imagine if we take an electron with a Lorentz factor of 10 to 5, it will be boosted by 10 orders of magnitude. It's assustado. Eu penso que é assustado isso. So this is a very effective way of producing gamma rays. Okay. Well, okay, it's maybe not that effective because the amount of scattering is relatively low in AGN jets. However, you can really boost the energy of the photons. If we are working with flat spectrum radio quasars, there is another boosting factor, because you can, but we can get there later. You can imagine that in the jet of an AGN, I have a cloud of relativistic electrons, okay? But this cloud in the jet is moving with along the jet, okay? So we have a boost for them moving along the jet, but if the photon interact with a relativistic electron in the cloud, it will receive the square boost of the electron in the cloud and the boost from the jet. It's more complicated, but I can show you in the next lesson. But that's it. That's it. So what time is it? Let's continue here.